We continue in our chapter on Introduction to Trigonometry. In section 3.5, we will visit the basic trigonometric identities. Those are provided in your formula packet on the second page. And we will be looking at those identities in this section. First, we will start with the Pythagorean identities. The Pythagorean identities say that there is a relation between x, y, and r in every angle rotation, whether you are on the trigonometric circle or not. Now, of course, here you can see the trigonometric circle, but let's assume that this is any kind of circle for a rotation. I have a random angle theta. I pick a point on the terminal side of theta. It has coordinates x, y, and the distance from the center of the circle from the origin is equal to r. And r doesn't have to equal 1 in this particular case. We can be in the general case. So if I try to find the expression sine squared of theta plus cosine squared of theta, from the definition, sine is y over r, and the cosine is x over r. And then that will be y squared over r squared plus x squared over r squared. These are fractions with common denominator. And you know that as we have discussed, when you create this triangle that is attached on the x-axis, the vertical distance of the point on the terminal side from the x-axis will be your y-coordinate, and the horizontal distance will be your x-coordinate. And y squared plus x squared in the right triangle created equals the hypotenuse squared. So the numerator is actually r squared. And therefore, r squared over r squared will equal to 1. This proves the first Pythagorean identity. To prove the other Pythagorean identities, I can also do it with the definition of the cotangent and the cosecant, but I can use an identity that I have already proven and do some algebra to that. So I will divide all three terms by sine squared of theta. This means I'm dividing both sides of the equation with sine squared of theta. And sine squared over sine squared will equal to 1. The cosine squared over the sine squared, I'm going to come here to prove this identity, is equal to the cotangent of theta. Why is that true? Because the cosine is x over r, and the sine is y over r, and the r will simplify, and that will give me x over y, which is the cotangent of theta. So this will be x squared over y squared, which is the cotangent squared of theta. And then 1 over sine theta, I'm going to come and prove this identity, equals the cosecant theta. And why is that true? Because the sine theta is y divided by r, and the reciprocal of y divided by r is r divided by y, which is the definition of the cosecant. So that is cosecant squared of theta. And that proves the other Pythagorean identity. I can also take the original Pythagorean identity, sine squared of theta plus cosine squared of theta equals 1. And instead of dividing by sine squared of theta, I can divide by cosine squared of theta. Both sides, all three terms, and I will get a 1 here. The sine squared over the cosine squared is actually the tangent squared. Why? the tangent is equal to sine over cosine. Y over r divided by x over r is y divided by x when the r's are simplified, which is the definition of the tangent. So this is the tangent squared of theta. And 1 over the cosine is the secant. And why is that? The cosine is x divided by r, and the reciprocal of x divided by r is r divided by x, which is the secant theta. So that will be the secant theta squared. So these are the two Pythagorean identities that you can use after we have proven it here. And similar to the identities that we proved earlier, these 4, there are even more, and you can try to prove them yourselves using the definitions for the functions, trigonometric functions of any angle, to show the ratio identities, which we just proved for tangent and cotangent, but also the other reciprocal identities, that the cotangent is the reciprocal of the tangent, the cosecant is the reciprocal of the sine, and the secant is the reciprocal of the cosine. These also are true for the sine, the cosine, and the tangent. So you can take any identity, let's say cosecant theta is 1 over sine theta, and solve that for the sine. So the way I'm going to do it is I will cross multiply sine theta times cosecant theta equals 1, and then I will divide by cosecant theta, and I will get that the sine theta is the reciprocal of the cosecant theta. So I can prove in a similar manner the ratio, the other reciprocal identities. Another very important group of identities is the cofunction identities. I'm going to put some stars here on those. We have some additional videos created in our Lumen course and also in my YouTube channel regarding cofunctions and coreference angles. I will prove the cofunctions for you on a right triangle, and then I'm going to give you a preview of what that looks like on the plane for any angle. But you should be watching the video on my YouTube channel on coreference angles. So when you have a right triangle, and you have an angle theta here, the other acute angle, let's call it phi, is the complementary of theta. It's equal to 90 degrees minus theta or pi over 2 minus theta, depending if you have theta in degrees or if you have theta in radians. And the property that they have is that if for theta A is the opposite, this side A is actually the adjacent of phi. And this side B is the adjacent of theta, but it is the opposite of phi. And then the hypotenuse is the hypotenuse for both of them. So if I want to do the cosine of theta, which will be the adjacent B over the hypotenuse, I'm going to call it hypotenuse, that will actually be the sine of phi, because the sine of phi is the opposite of phi, which is B, divided by the hypotenuse. And the sine of theta, which will be the opposite of theta, that's A, divided by the hypotenuse, will be the cosine of phi, because A is the adjacent of phi. And the tangent of theta which will be the opposite of theta, A, divided by the adjacent of theta, B, will actually be the cotangent of phi, because A over B for phi is adjacent over the opposite. So these two complementary angles, theta and phi, have the property that their cofunctions are equal to each other. So the sine of theta is the cosine of the complementary angle. The cosine of theta is the sine of the complementary angle. The tangent of theta is the cotangent of the complementary angle. The cotangent of theta is the tangent of the complementary angle. The secant and the cosecant are cofunctions. They swap values between theta and phi. Theta and phi being two angles that add to 90 degrees. Why is that? Because in their definition, the adjacent and the opposite swap between those two angles. Now, how does that look like on the plane? And again, I'm not going to go into detail here, but I'll give you a preview. So on the plane, the reference angle, if theta is a reference angle in any quadrant, remember the reference angle will be a positive acute angle that you make with the x-axis. So you will have here an x and a y and an r. Your phi angle will actually have the same reference angle, but that angle, theta, will be referenced on the vertical axis. So if phi is 90 degrees minus theta, then theta is your reference angle with respect to the vertical axis. And in that case, if I were to draw the same rectangle, this x prime equals to the y of theta, and this y prime of the complementary angle will equal to the x of theta. So basically you will have the triangles attached to different axes be equal or congruent to each other. Therefore, these guys swap their x and their y coordinates. The same way in the right triangle, they swap the adjacent and the opposite sides. On the plane, they will swap the x and the y coordinates. Therefore, the cosine of theta, which would be x over r, will equal to y prime over r, but y prime is the y of angle phi, and that will be the sine of phi. And again, phi is from the x-axis to the terminal side of this angle that happens to have theta as its complementary angle. And then the sine of theta will be y divided by r, but here we saw that the y is equal to the x of the angle phi, so that will equal to x prime over r, and x over r for phi is the cosine of phi. And the tangent of theta will equal to the y over the x in the triangle that is attached to the horizontal axis, but that will be equal to the x prime over the y prime for the triangle that is attached to the vertical axis, and that is the cotangent of phi. So again, you can prove each one of them separately, and you can prove it in a general case. The last part of the identities that we have in our packet and we want to work on is what we call even and odd identities. These are functions. So the sine, the cosine, the tangent, and the other three trigonometric values are actually functions that we will be looking at later on in this chapter. And if you remember from unit 1, we discussed symmetry and even and odd functions. So unit 1 was a review of college algebra. And we said that even functions have the property that opposite x's have equal y's, and odd functions have the property that opposite x's have opposite y values. So the trigonometric functions have the property that some of them maintain their value for opposite rotations, and these are the cosine and its reciprocal, the secant. So if I rotate theta degrees in a positive direction, and if I rotate theta degrees in the negative direction, then the x coordinates on the unit circle, or x over r, if I'm not on the unit circle, for these opposite rotations are equal to each other, because in a point in quadrant 1 and it's symmetric in quadrant 4 have the same x value. Of course, it doesn't have to be in quadrant 1. It could be that I have a theta here in quadrant 2, and the minus theta will be the symmetric in quadrant 3. But again, these guys have still the same x divided by r. So x divided by r is the same for theta and negative theta. However, for the sine and the cosecant, this is the y value. We are looking for y over r, and the y values are opposite of each other, because when we are reflecting about the x-axis from quadrant 1 to 4, this y is positive, and this y prime, let's say, is negative, but in absolute value, they have the same value. So the one y is the opposite of the other y, right? So the y prime will equal to negative y. So if I'm looking for the y over r, that will be the sine of theta. And the y prime over r will be the sine of negative theta, but that will equal to negative y over r. So it will equal to negative sine of theta. And therefore, the sine is an odd function, and it will be the same if the angle was in quadrant 2 and the negative angle would land in quadrant 3. So we would have the same situation. So we would have an angle theta this way, this is the y, and then we will have its opposite angle, negative theta this way, and that will be minus y. For the tangents, it's the same idea. So again, when you have theta and a negative theta, you have the same x, but you have a y and a minus y. So y over x is the tangent of theta, and negative y over x would be the tangent of negative theta. And you can see that they are opposite of each other, right? So the tangent and the cotangent will be odd functions. One other set of formulas that we discussed earlier, but they are stated explicitly in our packet, are the periodic functions. Periodic functions are functions that actually repeat themselves. And they are very interesting to observe. And we don't have a part in the notes to deal with that, but I would like to discuss them with you. So when we have a cosine or a sine, and it's reciprocal, secant or cosecant, then since the sine and the cosine are equal to each other, the sine and the cosine equal to x over r, we observe that if we are at a particular location, the cosine, when we complete a full rotation and come back to the same location in a coterminal angle, that will equal to the cosine when we were there in the first place. So this results in a concept that we discussed in a previous video that said that if you are at a particular location theta and you add k times 2 pi, which means k full rotations of 360 degrees, you will end up in the same location on the circle. So that if you are here and then you just add a 2 pi, or if you subtract a 2 pi, or if you add 3 times 2 pi, you will always end up in the same location. So you will end up having the same sine and the same cosine because you have the same x, y, and r. So the sine, the cosine, the secant, and the cosecant are periodic functions, and they repeat their values every 360 degrees. The tangent and the cotangent, and we will see that in a future video as well, actually repeat themselves every 180 degrees. And the reason this happens is because when you are in a particular location on the circle, the location in the opposite of the diameter of the circle actually is symmetric in terms of x being either negative and then switching to positive, and y being positive and then switching to negative, or x being positive and y positive and then switching to positive and negative. So the fraction y over x or the fraction x over y will actually repeat itself every time you hit a diameter. And you hit a diameter when you have the rotation of a straight angle. And the rotation of a straight angle is 180 degrees or pi. So this is k times pi, meaning that after half a circle, you will be in a situation that x and y will have the same absolute value, and they will also have switched signs in a way that you will maintain the ratio of those. We will do some applications in a future video.